Filippo Colomo, and he will speak about the Arctic curve fluctuations in square ice models. Please.
Thank you very much. It's for me great pleasure and great honor to be here to celebrate Philippe. Actually, I met Philippe for the first time in '94. I remember it was in the office of Andrea Cappelli. Philippe was visiting Andrea in Florence. But then we did not cross so much until a workshop, a semester organized by Christian Kratenthaler in Vienna, and after that we intersected quite more. So this is joint work with Andrei Pronko from St. Petersburg, and I will speak about the fluctuation of the Arctic curve in my favorite model, the 6-vertex model. And this I will speak about is definitely about the square ice case, that is delta equal 1/2 A equal B equal C. Sorry. Okay, so very fast I recall that the 6-vertex model is a model of, for instance, of paths on a square, on a tetravalent graph. And since I will be interested in the case of fixed boundary condition, I have essentially can restrict to the symmetric case, that is the 3 different Boltzmann weights. And I can see the configuration as paths flowing through my square lattice. And the fact that the paths do not interrupt themselves but continue from one boundary to the other is what is called, implements the ice rule in the original arrow formulation. So as said, I will restrict on A equal B equal C or delta equal 1/2, because for some reason, in that case, calculations are simpler. Indeed, this is a full diagram of the model. Essentially, a lot is known when delta equals 0. And this is a critical phase. You have, of course, here some ferro and anti-ferro and negate ferro electrical regimes. And as I said, here everything is much is known because it's a free fermion point. Here things are quite complicated, and here as well. Here a lot is known because in terms of stochastic 6-vertex model, or in terms of ASEP, which can be seen in these regions. And the case I will consider is this delta equal 1/2, where you have combinatorics and some simplification in all this expression. It is related to these other ones. These are 2 combinatorial points related to Razumov-Stroganov, etc. So I will stick to this particular choice of fixed boundary condition, which are called domain wall boundary conditions, where all the paths flows from the top to the left. And why I'm interested in this? Because we have Arctic curve or limit shapes. Indeed, the boundary induce macroscopic order deep into the bulk, but you have tuned the parameter of the model to a disordered regime, so there is some competition. And actually, the entropic part of the free energy favors this kind of configurations. So here you have what you call, in the scaling limit, when the size of the model tends to infinity, but the number of sites, but you rescale the mesh to 0 in such a way to have a finite domain. This last pass, with this last pass, yes, will tend to some to a curve which separates the 2 phases, the disordered and the frozen domain, sharply. And this curve is called the Arctic curve. And of course, you can also be interested in the fluctuation of this Arctic curve. So actually, the Arctic curve depends on delta. Here I show you 2 relatively recent simulations. You see that the red is just a guide for the red curve is a guide for the n I, and it's related to the delta equals. It corresponds to it's a circle, and it corresponds to the delta equals 0 case. While the blue line depends to is related to -1/2 or -1 in these 2 cases. And of course, the exact analytic expression has been around for some time. And in the case delta equal 1/2, things are simpler, and there is even a rigorous proof provided recently by Agarwal. What else? Yes, next question, fluctuation. So Here the fluctuation, you can forget about the fact that it is a delta equal 1/2 simulation. I had no picture underhand, but you can let us restrict to the delta equal 0 case first. So this is delta equal 0, you have this fluctuation, and you want to describe them. And actually, you can consider two different statistics. The most natural one may be you here just draw a diagonal, and you look at the intersection of the most external path with the diagonal. This will be some points. And when you consider different sample, you will have fluctuation, and you want to study these fluctuations. Another one is instead you stay in the vicinity of the diagonal here, and you look at the local maxima. It is like if you want to probe this with some suitable test function. In one case, you are probing with a square. You ask what is the probability of having a frozen square here. And in the other case, you are asking what is the probability of having a frozen triangle. These two cases are known to be related, in the free fermion case, to two different random matrix models. In the GUE case in the first case, and in the GUE ensemble, and in the GOE ensemble in the second case. But actually, for free fermion and determinantal process, etc., you can indeed show through these papers, and when you observe for the first statistic this distribution, then the second will obey this one. So this is a theorem, let us say. All this has been shown quite in detail by Johansson, and everything is known at delta equals 0. When you go beyond delta equals 0, not much is known. Actually, there is something which is known in the case I have shown you before, ASEP, stochastics, but for generic delta below 1, actually there is not much. There is some numerics, recent numeric made by these two groups. And indeed, if you plot, for people which are not really expert about residuum, if you plot residuum and you plot the error function, the cumulative residuum of the error function with Mathematica, you almost see no difference. They are almost indistinguishable. And if you take the probability distribution function in the Gaussian or the residuum f prime, again you see almost no difference if you consider the same mean and variance. But if you take the logarithm, in one case you will have minus x squared, which will be a parabola. Since it is in the tails of the distributions that you have big difference, here you have residuum, and instead you would have something quite different here on this side. So the convergence to residuum is quite convincing here. Sorry?
Even before the distribution, you have a critical exponent, 1/3. Is there evidence for it that you have a 1/3 exponent for the scaling exponent?
Well, in which sense? I mean, I did not mention it yet 1/3. Sorry. Say it again. Yes. You look at the scaling. Well, the scaling is related to the fact that actually, in the delta equals 0 case, you can map this. The points on the diagonal are really governed by a random matrix model. You have a density which goes as square root, and you have the usual argument which gives you that the fluctuations are of order 1/3. For delta equals 0, there were preliminary calculations which were mentioned here, yes, which indeed really shown this delta equal 1/3. Okay, no, so this is okay. I mean, it's very convincing. The numerics is under control. And also there is a theorem, a recent theorem by Johansson, IPhT and Johansson, which shows that the second statistic I have mentioned above indeed obey the residuum 1, this GOE ensemble, for the maximum of the most external path. And so, you know, GUE implies GOE, but not vice versa. But anyway, it is some hint. Anyway, GUE is still resisting. So I will try to convince you that GUE is here, but it is an exact result, but it is non-rigorous. So let me introduce a few ingredients. So this is the partition function, just to introduce the notation in some sense. I put a red dot when I constrain some edge to be empty of any path, a thick edge when there is a path, and when there is nothing, this means I am summing over all possible configuration with that boundary condition and that, and compatibly with the 6 vertex Rice rule. A very important ingredient in the next few slides will be this quantity, which is the one-point boundary correlator. Since if you look at the first row, you have all this line entering, one is getting out already in the first horizontal line, so you will be left with one empty edge. And this empty edge can be at any position here. You can ask what is the probability of having it at position R, and you call this boundary correlation function. And just as the partition function was computed as what is now called a Diselgi-Korepin determinant or Hankel determinant in the homogeneous limit, here you have something similar. You have these representations, but they are deformed in the sense that the last column is different. So the object becomes more complicated to calculate if you want to extract asymptotics or things like that. Then the most interesting object, something which for people coming from random matrix theory, this is essentially the gap probability. So I call it emptiness formation probability. It comes from, there are analogous quantities in quantum spin chain. And we are just asking for the probability of having a rectangle with this corner at coordinate R and S, R horizontal, S vertical, to having such a rectangle to be frozen. Of course, if R and S are near this corner, the probability will be 1. And as soon as we enter the disordered region, it will start to diminish and it will become 0. In the macroscopic limit, this behavior will be stepwise. It will be a step function from order to disorder. And indeed, some multiple integral representation have been provided by André and myself over the years. But, well, you do a lot of work and then you don't know what to do with this multiple integral representation. With some heuristic, we managed to extract the Arctic curve because we were looking for a stepwise behavior. This was easy, relatively easy, but you cannot do much asymptotic with these objects. I will show you how these objects are built. You will see they are a bit complicated. So I have introduced the boundary correlation function. We just build the associated generating function, which this being a probability when we sum over all R, that is when we put z equal 1, it is normalized to 1. Then we build this determinant, where these H functions are a kind of complicated object because the coefficients here are this modifier Diselgi-Korepin determinant. So this is in principle just a multivariate polynomial. You divide by Vandermonde, so it is completely symmetric. But in practice, the coefficient of this multivariate polynomial are products of deformed Diselgi-Korepin determinant. And you don't know really what to do with this. But they enter as a special ingredient because this can be seen as an alternative expression for Diselgi-Korepin determinant related to the original one through some de Nanou-Jacobi identity. It enters in quite a natural way when you build this multiple integral representation for EFP. So what is this CFP? You have some factorized measure, let us say, in the language of random matrix. Here you have some Vandermonde, but you have this denominator, which for delta different from 0 is you don't know what to do very much with this, and also you have this complicated polynomial. So when delta equals 0, what happens? This and this essentially cancels. Then you symmetrize with respect to J, and this will become a square Vandermonde. And you have just a standard random matrix model in GUE, and it's quite obvious to obtain Tracy-Widom, etc. And you can do in several ways. For instance, you can make this integral partially and rewrite this as in terms of Meixner polynomial. And then you just reproduce the result of by Johansson. and you obtain F2.
Filippo, why square van der Monde? I see only first degree.
Because here there is some J, so this is not symmetric.
This is you have
When you
another
symmetrize, you obtain
van
a
der
second one.
Monde.
Okay, yes, so from what I will, this is just a repetition, sorry, let us avoid this. Let us say that now I will try to see if we can analyze the asymptotic behavior of this expression in some particular case. The particular case is delta equal 1/2, but what I will say, part of it still hold for genic delta, so I will tell it in hope of future generalization. So to start with, we just put t equal 1, this is not really important, and we limit ourselves to the case in which the frozen rectangle of PFP is a square.
So what was the t?
The t was b over a, it was a...
B over a, okay.
Okay, it's just a secondary quantity. And we redefine this emptiness formulation probability for the case in which the frozen rectangle is a square, S by S square, in the northwest region, okay? And then we just make a change of variable. We have this contour at infinity. And just for a future notation, I rewrite the integrand in this way. Not much has changed. But what we can do now is to shrink down these contours to the poles. We have pole at 1, at 0, and this one. These one are a kind of nightmare, but here some miracle happen. Part of the miracle is quite obvious in the sense that some of these zeros are actually of these poles are cancelled by 0 inside, and this is quite natural from the construction. Some others give a non-vanishing contribution, but when integrated over the other contour, they vanish. So all these poles do not contribute, and we are left only with the pole at 0 and 1, and so our EFP is written in this way. And then you have to sum over all possible contribution when you take all 0 or all 1, and that's quite standard. But, so we start with two lemmas. The first lemma is, let us take everything around 1. It just, you can make the calculation, it's just 1, it's easy to prove. Just to give you a flavor of the idea, here you have this j, you put, consider j equal s, so in the variable zs, you integrate, you have a simple pole in 1, you put 1 everywhere here. Since this quantity, when zs is 1, becomes just the same quantity with 1 less variable, you really observe that you obtain the same integrand with 1 variable less. You iterate, and you obtain 1. In the second lemma, you have the similar things around 0, but there is a big difference. These always hold. This holds only at delta equal 1/2 and t equal 1, and for the square EFP. This is more general. So this is quite restricting. This is a crucial in what we will say in below. So that's why our result hold only in this case. So, and when here, sorry, in this sum, so we have k equals 0, we know how to do it, k equals s, we know how to do it, but what to do when k is generic? When k is generic, we have some integral here around 0 and around 1, and we must remember, well, we see that what will happen, we will have here some product of this function a, this is a determinant, remember. So this will be product of s function of type hn with some shifting indices coming from this. And then you have poles at 0 and 1 of high order, so you will have derivatives of this evaluated at 0 and 1. This makes a lot of objects, actually. If you try to compute them, you really see that you have about s square quantities, and well, we shall see that this is not nice. So the problem is that now we want to guess some equivalent representation for EFP, which here is more amenable for asymptotics. So this guesswork can work only if your expression do not depend on too many objects. Otherwise, you will never recognize any structure. So we need to reduce this s square quantity to a more reasonable number. And indeed, there are a lot of identity around. I show you someone. But they come from the fact that you have different representation for the same object, and so you have obvious identity which come from this, and actually they are related to the Yang-Baxter algebra of operators in this model. Then we have a second set of identities, which is related to the fact that when delta equal 1/2, you are related to the problem of alternating sign matrix. You know what is exactly, this determinant can be exactly evaluated, and they appear to form hypergeometric numbers, and this Hn of z is just hypergeometric function, and you have then many more identities again, which are, you can find them on Gradschein, for instance. So with the help of this identity, you can reduce all your evaluation of multiple integral from to depend, instead of S² object, just a much smaller number of objects, 2s-1, which are these ones. Okay, so it is, when I don't put the variable here, it's because I consider it to be 0. So I have exactly 2s-1 quantity, which are this quantity shifted in the main in the index, or this quantity with a variable number of derivatives. So, inspired by Tracy Widom, we want to rewrite our multiple integral as a Fredholm determinant of some matrix at the moment. So this will be just a S by S matrix. And we want to guess what is the structure of this S by S matrix in such a way that we have this identity, whereas here we have our multiple integral representation. Two ingredients which will play a role in below. One is that we will use this decomposition, slightly different from standard, this diagonal lower and upper triangular matrix. This simplifies the calculation, and it appears to be this one to be more useful than others. And another fact is that we can guess part of the structure of this matrix A at order S if we already know the structure of order S-1. So we observed that we can make these ansatz in general. So we know the structure at S-1. We just make a shift in the indices, and this will be the S-1 times S-1 block of the bigger matrix at order S. And just because we will have to play some Sudoku to solve this problem, let me introduce some simple notation. So this function A, Hn, we shall keep track only of the shift in the indices. They are all evaluated at 0, remember. And this k is k prime, k second is essentially this ratio of derivative of the function h. So we have these two S objects, and we start. Case S equal 1 is very easy. We have two contours, we evaluate the pole, and of course we obtain this result. And I recall you that we have just introduced the notation that this is B0, and we obtain simply this, which we already know from our two lemma, in fact. Our two lemma were saying E0 is always 1, and D1 is just a product of B's. And just by identifying A, just B0. S equal 2, it's already, you know, to calculate this integral, it's already some work, because it's double, but you have all these poles, etc., etc. And you must check that the spurious pole give indeed vanishing contribution. And, well, you use the identity to reduce the number of objects. You use the fact that the determinant of 1 and minus A can be expanded in trace of power of A, and then you have just to solve these two equations. You have several solutions in principle, but it appears that if you find one, the others are related, at least in this case, to similarity transformation. So we build this function A, which is in this way. We verify that the determinant is a product of B's, and then you have this structure. Well, we did this for S equal 3. Again, the identity I showed you were instrumental, were essential in building this. And for S equal 4, I spare you the calculation. And so we are not able to go further, so now we have to guess some structure. And so the structure we guess, here we do not see much, but if we concentrate on the, here on the odd lines and here on the even columns, if you spend enough time about this, you will recognize that this is a Laguerre polynomial. In this way. But when you look at this, they are not as much as Laguerre. So you have to work a little bit, but indeed, again, they are Laguerre. If you remember that you have also associate Laguerre polynomials, and they can be written as difference. So the red entries at the moment are Laguerre. These are difference of Laguerre polynomial. It's not completely symmetric, but it appears that we have some identity with associated Laguerre polynomial. So for the first, for the red row, we can use this identity, and for the red row, we have the sum. For the blue row, we have just the difference of the same object. So we are led to make this conjecture. This conjecture, which we have built by hand for S equal 1, 2, 3, 4, is quite bold for generic S, because you could say, well, your problem is underdeterminate. Maybe what you have said is okay for the 4 case, but when S equal 5, will still your ansat solve the problem, etc., etc. And one thing, it is quite natural that you have Laguerre polynomial, because Laguerre polynomial, there is this hand that, maybe it was you. No, okay, no problem. What should I do? No. Merci. So yes, a Laguerre polynomial enjoys this nice identity, and if you recall our multiple integral representation, we had this function h multiplied by power of z and power of 1 minus z, so it's quite clear that you have this kind of structure. And yes, here I put r for brevity, to be short. To be short, but you should remember that r is not independent, it's also n minus s. So this I rewrite in a slightly different way the conjecture here, and I just use backwards the Laguerre integral, and we have this nice expression. And we recall that in the S by A case, this is an S by S matrix. And when S increases, you have to build the whole matrix because the index are shifted somehow. Okay. So, well, I have already said many of these things about this ansatz, which was crucial, these identities, which was crucial, the fact that this is still a guess, and so we are really seeking for a proof, and and also we are unable, you know, for the S equal 4 case, we could not have done it without using Mathematica to keep track of things, because it's really hard work. So what to do? Well, what we can do is, of course, to check the case S equal 5 with Mathematica. And indeed, we did this. We did this, and I would say it worked quite well. So we put S equal 5 and n, well, when n is smaller than 9, by definition, by construction, EFP will be 0. And when n increase, you obtain this number, which is essentially a ratio of alternating of enumeration of alternating symmetrics without or with a block of 0 in one corner. And just a folklore note, to calculate, for instance, this number, Mathematica takes a few minutes, the one obtained from the determinant. When you compute it from multiple integral representation, this took 4 days. So if this is good for Mathematica, maybe it's also good for human when you want to evaluate asymptotic, etc., etc. It is already a big advantage to have this expression. So how much time do I have?
15.
Okay, yes. So when you have, well, I emphasize, well, as even if the matrix A that I have shown you in the conjecture is finite, the structure of the determinant is the type 1 as 1 minus A something. And when you have 1 minus A something and you have integrals, like here I have just added one integral, and you have integration in this way, you can play with these indices and with this integral to split your matrix in 2 pieces And what is important is that if you find some integral operator, linear integral operator, whose kernel, whose powers, your matrix A, your freedom determinant can be defined in terms of expansion, in terms of trace of power of A. See if you find some other operator or matrix or whatever, B, whose power have the same trace, for which trace of A to the n is equal to trace of B to the n for any n, then you can build the corresponding freedom determinant. Here, this is what we did here. We introduced this integral, it's just formal. We exponentiated this denominator. And then we trade this sum with this integral. And what you obtain is just a freedom determinant, which is acting on whose kernel is acting on the positive real axis, and which has this expression. Now we have this sum here. So once you, well, now what I will tell from now on is completely rigorous once you admit this representation red star, okay? So we have this kernel, which it's maybe complicated, but you know, when you have a kernel in this way, it's much simpler to compute any asymptotics, because you have not an S by S determinant or a S-fold integral. You have just a freedom determinant with some kernel, and the kernel depends on S in an analytic way. For expert, I would say that this kernel is not of integrable form in the sense of its and collaborators. And so, for instance, all these techniques from Riemann-Hilbert matrix problem, matrix Riemann-Hilbert problem, etc., cannot be easily applied. At the same time, this is not a free Fermion model, so in some sense, this is not a surprise. So let us do the scaling limit. What is the scaling limit? As I said, we introduce some finite parameter y, which in our case will stay on this interval, and we rescale. We replace S with this y times n, and we send n to infinity. That is, we rescale everything in this scaling limit. And what will happen in this case is that, you know, this is a frozen square of FP. If y, which was originally S, is not too big, this will be 1. If y is greater than some critical value, it will go to 0. And what we want to show is that the way this crossover is actually governed by traceability. And this yc can be computed from the knowledge of the Arctic curve, and it is given by this expression. Okay, so what you do, you just replace, you have this function h, you know this asymptotic behavior, you replace, you do a very standard analysis, a saddle point analysis of this model. You have this function g, it's a double integral, and this is a function, the actions that you have to derive to find the saddle point. You derive and you find actually that you have two solutions. The two solutions can be both real or complex conjugate, or can collide for some critical value y. So the fact that the critical value y for which they collide is exactly the critical value which is known from the Arctic curve is a strong, it's a very good result to support our conjecture, I would say, because this was not at all. If one could say, you know, you take any kernels and you do asymptotics. If the kernel has been chosen sufficiently intelligently, you will always obtain traceability. Yes, but it's not obvious that the critical point will be exactly where you expect it. Okay. And also, when you do the saddle point analysis, when the 2 points are real, one is closer to the origin where you are integrating, your contour was near the origin. And so this will be the denominating one, and it will give you some exponential decay of the kernel. And instead, when you are inside the disordered region, when y is larger than yc, what you see is that they are complex conjugates, so they both contribute, and the behavior is oscillatory, and indeed this is what you observe in dimer model in the delta equals 0 case. Here, so this is in complete analogy with the work of Kenyon, Kunkov, and Sheffield for dimer models. Then when I am just closing, I mean, this is again very standard. You expand your action in the vicinity of the double critical point. It's very standard. You keep the first and the third order term. You have to rescale them in such a way that they can compete, and the correct scaling is this one. And you have to integrate in the vicinity of these two saddle points, which are very close and close to this point 1/2. And you know that the contribution to the integral is given by this. You deform the contour appropriately. And what you have, then you rescale, etc. And what you have for your kernel is essentially this. Already here you see some airy. And indeed, it's just a change, well. So to summarize what we have done, yes, let us take, we recall that our conjectural expression, where A is an S by S matrix, and we compute its determinant, and we put S rescaled in this way, that is with the we shifted to be just in correspondence of the Arctic curve with some rescaled variable sigma in this way, which scale then to the 1/3 with some appropriate coefficients which came from our asymptotic analysis. Well, what we obtain is that in the large n limit, this becomes as the Freedom determinant of this operator, which I wrote, whose kernel is written here. Okay, so it is really a student exercise that this can be rewritten. Note that here we're integrating between 0 and infinity, and the variable sigma is inside the integrand, but it's very easy to show that you can rewrite it. Again, you can trade 0 and infinity with sigma and infinity, and you recognize here the airy kernel. So what you have shown is that our starting quantity, indeed, in the scaling limit, goes to F2, to the GUE Tracy-Widom distribution. So, to conclude, what we have, it's a conjecture here. This is for Philippe. And then we have a theorem. I mean, this matrix A is such that it's free in its determinant in the scaling limit behaves in this way. So this is these coefficients are non-trivial and are in full agreement, first with the numerics, and second with what we know from Arctic curves. This is exactly the intersection of Arctic curve with the diagonal, and this is related, if you believe in KPZ, this is what you would expect, KPZ theory, this is what you would expect and can be computed from the curvature of the Arctic curve. And moreover, our result implies via this Corwin-Castell-Reminick paper that the maximal deviation are governed by GOE Tracy-Widom distribution, as proven by this guy, and the numerical coefficients are in complete agreement with the one found here. I mean, they are different, but the correspondent is the correct one. So I have finished, and just to conclude, I want to show you two young guys strolling in the mountains of Santa Monica quite recently. Buon anniversaire, Philippe.
Questions? Proofs?
Proofs. The next talk.
Hi, Filippo. So I was wondering, you have a matrix A, and when you go to a linear operator K theta, yes, you describe the construction. So how specific is it to a form? Would you recall the form of a matrix A you have, and how specific is your construction?
Well, the construction is that when you have, if you have some matrix which is of this form, I write my matrix A in this form. You can sum over alpha. In that case, it was an integral, but it's the same. It's clear that let us call this A tilde, and this will be B tilde. It's not a good choice of letter, but as this is EJ and this is alpha beta. So I don't know if it is clear that any power of this and any power of this will have the same trace. That's the point. Okay. Did I answer your question?
Yeah, okay. So,
yes. So you use this trick. Actually, we use this trick a couple of times at least, also in the last step to recover the true airy kernel. This is very standard trick when you have freedom determinants.
Okay. Thank you.
It's maybe half a question and half a remark. You have talked repeatedly about numerical evidence, but I have the impression that you have mixed numerical evidences which are very different between each other. The numerical simulation of Correpin, VT, and so on, well, I can believe it, but the list of rational functions, rational numbers this way, it's a huge numerical evidence. That one is killing the problem of numerical evidence much more than doing numerical simulations. Am I right?
Well, the numerical evidence of my EFP, I mean the one done with Mathematica, says the EFP, the alternative EFP expression that I have provided is the same as the original one for S equal 5. While the numerics given by Prauer-Spon and by VT, etc., is saying something different. We analyze the simulation. This is an histogram taken from numerical simulation of the SIG vertex. You take 5,000 samples in the case of Spon. 5,000 samples because you need to, you need to test the Q, so you need an enormous amount of data. And indeed, here, this is has nothing to do with my EFP. It has to do with the fact that, sorry, where was it? Here. You know, really, if you plot here the Gaussian, which you cannot distinguish on a normal plot, in this log plot, sorry, would be something like this. And if you look at the Qs, indeed, of course, this is the black one. The black dots here is this huge lattice, so they have not so many simulations here, so it is more difficult to test the Q. But if you have, if you consider the yellow or the blue again, you can go here and you see that the Q are really tested. The Q, I recall that the Q in Tracy Widom is like on one side minus x exponential of minus x cube of minus x to the 3/2.
Let me say that differently. Let me check if I'm right. When you said in your two columns of rationals that one took a few minutes and the other one took a...
Yes.
The one that took a few minutes, which is the conjectural one.
Yes.
You can do that, for example, s equals 6, n equal 14.
Yes.
And then you could compare that to the explicit counting of alternating set matrices of that size. Which is still doable. No?
I don't know. Do you know how many alternative matrices with a frozen square are there? I don't know.
Well, you have a formula for cutting alternating set matrix along a horizontal line. That one, no? The spin...
Yes. Yes, but I don't know if it's enough. But maybe we can discuss this privately. I'm not sure I have understood what you were saying.
Jarno?
Yes?
Yeah, Filippo, I have a question. For your conjectured kernel, you showed that in the leading order it gives the airy kernel, basically. You gave a double contour integral representation.
Yes.
That's equal to airy. Can you compute the first order correction? I don't know, 1 over n third, because that is known for the GUE airy kernel, and maybe you can compare if this would also agree.
You are speaking of the conjectural one or the original one?
Of the conjectured one.
In the conjectural one, we compute the n to the 1/3.
Yes, but I mean, if you compute the next order correction, so you just show the limiting order, but then the next correction will be, I don't know, 1 over n 1/3 or 2/3, and this is known also in the GUE.
Well, but here we are not really in GUE.
No, I know, but I mean, this
I would expect that the next correction would differ.
I don't know.
But I am not sure I am even able to compute them.
Okay.
I will ask for some reference, maybe tomorrow or this evening. Good catch.
Hi. Now, if you could comment more or again about this going from n equal 4 or s equal 4 to s equal 5. Why couldn't you do it? It's just too difficult.
No, for s, I mean, I have some formula. Then you can say, yes, but you have solved the problem which has infinite solution. You are showing me one, but we don't know if it is the correct one which solves all the constraints and indeed is equal to the original EFP. And I say, okay, let us do a check. Let us do a check. I use my conjecture, I compute it numerically, semi-numerically with Mathematica. The conjectural determinant formula, the original integral formula, I obtain the same number. This means that my guess satisfies at least s equal 5. I think this is a check you have to do. When you do a guess, you have to do a check afterwards. Otherwise, it's like best fit. You will obtain
No, but the guess, you check the guess for s equal 1, 2, 3, 4?
Well, yes, well, it's a theorem. For 1, 2, 3, 4, it's a theorem. I don't need to check the guess. I built it. I mean,
so my question is,
for 1, 2, 3, 4, it's fourth theorem. For 5, it's numerically verified. For 6 and over, it's a conjecture. Okay.
Thank you.
No more questions? Okay, so let's thank again Filippo for this inspiring talk.